Welcome to today's Explainer, Demystifying the Operating System. Right now, literally as we're speaking, the device sitting right in front of you is quietly pulling off a miracle. It's executing billions of microscopic instructions every single second. It's shuffling data, rendering pixels, checking the network, listening for your input, all at the exact same time. It's just a massive, invisible operation. But, have you ever actually stopped to wonder how it keeps it all straight? How does this little block of metal and silicone not just immediately descend into total chaos?
Seriously? How does it handle billions of simultaneous tasks without, quite literally, melting the processor into a puddle? We are constantly demanding more, right? More speed, 50 tabs open, insane high-def graphics. But hardware has very real, very unforgiving physical limits. There's this huge gap between the raw, buzzing electrical components inside your machine and that buttery smooth experience you see on your screen. And today, we're going to bridge that gap.
So let's take a quick look at how we even got here. Way back in 1945, John von Neumann laid down the computing architecture that we basically still use today, separating the processor from the memory. Fast forward to the 1990s, and we had a problem. Processors were just sitting around waiting way too long for data to show up from memory. It was a massive bottleneck. So engineers fixed this by slapping high-speed CPU caches right onto the chips themselves. Problem solved, right? Well, not quite. We eventually hit a literal physical wall. Pushing a single-core processor any faster generated so much heat it would destroy the chip. So around 2004, the industry had to pivot. Instead of building one blazing hot core, they started packing multiple, cooler cores onto a single chip. And that brilliant workaround sparked an evolution that leads straight to the massively interconnected supercomputers we use today.
Okay, so we kind of solved the hardware problem by throwing more cores, more memory, and faster connections at it. But guess what? That creates a brand new nightmare. With all these physical resources scattered everywhere across the system, how on earth do you actually control it all? I mean, you can't expect every single app developer to write custom code just to tell a specific piece of silicon how to hold one byte of data. That'd be insane. What we desperately need here is a software solution to manage our hardware solution. And that software solution? It's the operating system. By definition, an OS is the software whose entire job is to manage the computer's resources for its users and applications. It is the vital middleman standing between you and that raw, incredibly complex hardware. Honestly, without the operating system, your machine is really just a very, very expensive paperweight. To pull off this massive balancing act, the OS basically takes on three distinct personas. First up, it's the referee. It strictly manages all those finite shared resources. Like, it's the one making the call on which app gets to use the CPU right at this exact millisecond. Second, it's the illusionist. It casts this brilliant spell on every single application, making each app truly believe it has the entire computer completely to itself. And third, it's the glue. It offers standard, reliable services, think network connections or saving a file, so developers don't have to reinvent the wheel every time they build a new app. To really wrap our heads around how the OS orchestrates all of this madness, we're going to use this absolutely brilliant extended analogy from Professor Vivek Kumar. He maps the super abstract world of computer hardware to an ecosystem we can all easily picture: a bustling university campus. All right, let's start with your hard disk. In our campus, your disk storage is exactly like the university library. It is the persistent long-term storage facility for all your data and programs. Just like dusty books in a giant library, everything is safely stored here for the long haul, just waiting to be retrieved whenever a course actually needs it. Next up, we have the computer's DRAM, or central memory. Think of DRAM as the fast central servers where faculty store their active lecture slides for the current semester. It's way faster to just pull up a slide online than walking all the way across campus to the library, but the catch is it only holds the materials that are actively being used right now. But where does the actual heavy-lifting academic work happen? Well, the CPU cores are the university classrooms. Naturally, there are only a limited number of classrooms available on any campus. And inside those classrooms, you have the CPU caches. These are your whiteboards. They give you lightning-fast, immediate space to jot down information during a lecture. But the moment class is over, they are wiped completely clean for the next group. So who on earth coordinates this chaotic academic dance? The operating system is the university administration. The admins schedule absolutely everything, making sure the lights stay on and the rooms are perfectly booked without overlapping. And the applications running on your computer, those are the various degree programs, like, say, computer science or biology. And they are all fiercely competing for that very limited classroom time and resources. To keep this whole university from descending into total anarchy, the administration's daily grind boils down to 4 main goals: virtualization, concurrency, persistence, and protection and security. First on the docket is virtualization. Remember that illusionist persona we talked about? The OS acts as this master scheduler, rapidly swapping classes in and out of the limited physical classrooms. And it does this so fast, so seamlessly, that every single degree program operates under the absolute illusion that it owns the entire campus. It completely hides the harsh reality of how limited the resources actually are. Next is concurrency. A modern university runs dozens, maybe hundreds of lectures at the exact same time across different rooms, right? Well, the OS does the exact same thing across multi-core CPUs. It allows completely independent tasks to run simultaneously. But, and this is absolutely crucial, it has to manage dependencies. Just like a university timetable knows you can't take advanced robotics until you've passed Intro to Math, the OS makes sure things happen in the right order. Then we've got persistence. Look, at the end of the semester, you can't just leave your final exams sitting on the classroom whiteboard. They'd be erased in an instant for the next class. The administration makes sure that all critical grades and records are securely copied back to the library. In computing, persistence ensures your data is written safely to the physical disk. That way, you don't suffer a catastrophic loss the second someone trips over your power cord. Finally, number 4, protection and security. The administration has to enforce strict isolation. I mean, a biology student definitely shouldn't be able to sneak in and alter the grades of a computer science student. In the exact same way, the OS isolates applications from one another. It guarantees that one program cannot interfere with, spy on, or steal another program's data without explicit, verified permission. Now, while the campus analogy is awesome for understanding the theory of a smoothly running system, let's be real. The real world is a lot less forgiving. Modern operating systems actually live and struggle in incredibly distinct, often harsh hardware environments. Operating systems have to radically adapt depending on where they live. Take a desktop OS like Windows or Mac OS. Its main focus is high throughput, managing dozens of heavy, complex tasks all at once. But a mobile OS on a smartphone? Totally different beast. It's highly constrained and has to be incredibly lightweight to function on a much smaller memory footprint. And then you have real-time OSs, the ones inside embedded systems like heart pacemakers or anti-lock car brakes. These operate under extreme, literal life or death constraints, where tasks absolutely must be completed within strict timeframes, no exceptions. And this brings us to the relentless, behind-the-scenes battles the OS fights every single second. The first big one, high performance versus energy efficiency. The OS is constantly having to make a choice. Does it push the processor frequencies to the absolute max to run your game flawlessly, knowing full well it's going to generate massive heat and tank your battery? Or does it lean on efficient, slower background cores to save energy at the risk of a laggy experience? It is a non-stop tug of war. The second battle is dependability versus constant updates. As users, we just want a perfectly reliable system that is magically ready the second we open the laptop lid. But we live in reality, and in reality, software constantly needs disruptive bug fixes and security patches to stay safe. So balancing that dream of maximum uninterrupted uptime with the reality of mandatory system updates is a massive headache for OS designers. The third battle is complete portability versus hardware-specific optimization. Developers love writing an OS like Linux to be super portable, meaning it can just boot up seamlessly on virtually any random piece of hardware you throw at it. But there's a catch. The more generalized the code is, so it can work everywhere, the harder it becomes to squeeze every last drop of extreme performance out of one specific cutting-edge machine. All of this leads us to the ultimate, unavoidable truth of computing. Every single design decision is a trade-off. One single implementation of an OS simply cannot be optimized for all 4 of these challenges at once. You just can't have absolute military-grade security, maximum peak performance, endless battery life, and complete universal portability all at the exact same time. Something always has to give. Every OS you interact with has been forced to pick a different balance point to serve its specific purpose. So, I want to leave you with this. Take a second and think about the smartphone sitting next to you right now, or the computer you're watching this explainer on. Which specific trade-offs are running in your pocket today? What peak performance did your device secretly sacrifice just to save you an extra hour of battery life? Thanks for joining me for today's explainer, and as always, keep questioning the technology around you.